topic of this presentation is static electricity, and particularly the prevention of electrostatic discharges, or static zaps. The prevention of static zaps has long been known to be important in industries where flammable or explosive materials are used, in hospital operating rooms with explosive anesthetics, in chemical manufacturing facilities, especially those that make rocket fuel or gunpowder, around gasoline tankers, and even around solid fuel rockets on launching platforms at Cape Kennedy. What hasn't been known for a long time is that static zap can also cause failures in electronics. Recently, however, there has been growing concern for this for three reasons. First, we are using more and more plastics for packaging our electronics, and plastics are notoriously high static generators. Secondly, the state-of-the-art components that we are designing into our newest products are considerably more susceptible to static zap than the older ones were. And third, the cost of failures and the needs of our customers for high reliability are both increasing dramatically. To begin this presentation on static, I'd like to illustrate a few of the basic properties of static charge. Let me step over to the demo table to do that. Here I have a roll of ordinary Mylar mending tape, a notorious static generator. The first property of static charge is well known to all of us. We call it static cling. A statically charged surface tends to stick to another surface of the opposite polarity. The second property of static charge is that like charges repel one another. So if I have a second piece of tape of the same polarity as the first, it will repel the first piece. Even though it still is attracted to me, it is repelled by the like charge. The third property of static charge is that it creates a field, and we can measure these fields with static meters. Let me illustrate first with the zero-center analog meter. As I bring the charged tape near to it, you can see that it pins the meter, indicating a charge of more than 3,000 volts on this piece of tape. Similarly, the digital meter shows me a large charge on the tape and indicates that the polarity is positive. You may wonder now, how is this static charge generated? Going back to our slides, we'll illustrate the process of generating static charge. The most common way that static charge is generated is by something called the triboelectric effect, named for a Greek word meaning friction. Let's look at how the triboelectric effect works. The principle of the triboelectric effect is that when two materials are in contact, they will exchange charge, and when they are separated, one of the materials will end up positively charged and the other negatively. This characteristic that certain materials end up positive and others negative has been cataloged in something called the triboelectric series. What's important for us to know is that the human body, your skin and hair, and many of the materials that we wear as clothing are near the most positive end of that list, while the plastics that we commonly use for packaging are near the most negative end of that list. This sets the stage for trouble. I can demonstrate this effect at the demonstration table for you using my meter. Here I have some common plastics which we find in the office, laboratory, and production areas. The first is a rigid styrofoam coffee cup, a notorious static generator, and because of its high insulation resistance, it holds the charge for a long time, as I will now demonstrate. As you can see, there's more than enough charge here to peg the meter. A similar material is this white padding foam, which is often used to wrap electronic subassemblies. This material, too, is a high static generator, particularly when it's been rubbed or handled. More than enough to pin the meter. The third offender is ordinary transparent bubble pack, which becomes highly charged with handling or with vibration and friction. One particularly insidious offender is the ordinary plastic tube, which is used to ship and store integrated circuits. This is a high static generator, as I will now demonstrate. First, you see only a small amount of charge on it. If I handle it, then you see very large charges generated. One sneaky killer of electronic circuitry is the vinyl work order traveler, an example of which is shown here. These vinyl travelers can be charged up by handling, and should they be placed on or near a circuit, damage could result. Let me illustrate. As you can see, there is enough charge there to do damage. The last item I want to mention is an ordinary tool which is found everywhere. It's a desoldering tool made of ordinary plastic with a spring-loaded plunger in it. As you can see, it is slightly charged. When the plunger is released, it becomes more highly charged. Finally, insulating tools, such as these nylon tweezers, can become highly charged, particularly if they have previously been rubbed against some other material. So you can see that static charge is all around us on many of the common materials. Now, how does it get transferred to the components and assemblies? Once these high static charges have been generated by triboelectricity, the stage is set for a damaging zap. The way that this occurs is by a process known as induction. Let's look at the next slide and see how this works. In charging by induction, the charge on an insulator induces a charge on a component or assembly and can deliver more than one zap with each exposure. The exact details of the process are difficult to explain, but it can be easily demonstrated at our demo table. Here I have a small printed circuit assembly, typical of the kind that you might find in an electronic assembly area. As you can see, by looking at the meter, this assembly has no charge on it. However, if this assembly were packaged, for example, as I'm going to do here, lying on a piece of paper underneath a vinyl cover, even though the vinyl cover doesn't make contact with the board, when we remove the board and check it with the meter, we will find that it has become highly charged. The next time this board is grounded, that sudden discharge can result in a static zap. This brings me to the most commonly held misconception in the whole field of static electricity, so commonly held that I call it myth number 1. That is, that high humidity eliminates static charge. Actually, what happens is that high humidity merely reduces the static charge, using the film of moisture to bleed it off. You can see that even at an uncomfortable and sticky 80% relative humidity, we still can generate from a few hundred to more than 1,000 volts by ordinary activities of walking around the work area, and similar voltages by activities such as handling plastics or using ungrounded tools. The problem with humidity is that it reduces the static zaps below your level of feeling, which is 3,000 or 4,000 volts, not below the level of damage for components. We don't feel those zaps, but the components do. This brings me to the second most widely held misconception about static electricity, which is that only MOS parts are sensitive. Let's take a look at that belief. We have defined some classes of sensitivity for parts. Class 1 are those parts which are most sensitive. And just as you expected, MOS parts lead the list. However, advanced Schottky devices, junction FETs, and low-current silicon-controlled rectifiers, high-frequency transistors and integrated circuits, voltage regulators, and even thin-film resistors are sensitive to very small static zaps, much smaller than we can feel. Perhaps the newest member of the family are the very large-scale integrated circuits that have more than one layer of metal interconnections. These are very easy to damage with voltages of less than 100 volts. The second class of sensitivity are those devices which are more rugged than Class 1, but still can be damaged by a discharge too small to be felt. Even MOS parts with built-in protection networks fall in this class, as do Schottky diodes, linear integrated circuits, high-speed logic families, and even such passive components as monolithic ceramic capacitors. The least sensitive family of parts we call Class 3. Generally, you would feel a discharge big enough to damage these parts. And in this family, you find the parts we have used in our older designs, such as small signal diodes and transistors, the low-speed, higher power logic families, and such items as quartz and piezoelectric crystals. What you see is that nearly all parts are sensitive to static to some degree. And in fact, this becomes the keystone of our protection strategy. But before we go into that, I think that it's important that you know how to recognize these parts so that you will never again handle them incorrectly. Let's look at some photographs of some of these kinds of parts. Here is an example of a small signal transistor, in this case in an epoxy package. Here is a transistor in a metal can, and here are some axial-leaded components. One of them might be a silicon diode. All of these bipolar components can be damaged by static zap. When they are, we can look inside with a microscope, and this is what we see. The narrow fracture between the base and emitter pads of the transistor. There is now a short circuit between those two, and the transistor is no good. Another class of parts which is easily damaged by static are the integrated circuits. Here are examples of small-scale and large-scale epoxy packages, ceramic packages, metal cans. Often these are the ones for linear ICs, and small 8-leaded dual inline packages. All of these components contain very thin oxide layers, and this is what is most commonly damaged. Here is a photograph through the microscope of the line between a metal area and an oxide area, and you can see several small craters, each of which was made by a static discharge. If we increase the magnification, you can see just how spectacular these craters are. The items in the middle are bits of molten metal, which was generated by the discharge, and this whole crater is only about 1 micron across, but the parts are now worthless. Even passive components, such as these axial-leaded resistors, can be damaged by static zap. If we look inside to see what has happened, we see this area of metal film, which has been grooved in a spiral so as to make a long resistance element. Right here is the site of some static damage. Let's increase the magnification and see what it looks like. Here you can see it greatly enlarged, and you'll see that metal actually melted and formed a bridge across that insulating path, thereby changing the value of the resistor and making it no longer valuable. What you have just seen are examples of components which are known to be sensitive to static zap, and in fact some pictures of some of them which have been statically zapped. The problem is that there are many components which have not been tested, and also there are components which are only slightly wounded by a static zap, and they fail sometime later, perhaps once the product is in the customer's hands. For that reason, the only sensible approach is to treat all components as though they were static sensitive. This will simplify our plan of static zap prevention. Before introducing that plan, there is one more common misconception which I would like to discuss. I call that static myth number 3. The myth is that components mounted in an assembly are safe from static zap. In fact, nothing could be further from the truth. Components mounted in boards are more susceptible to zap than by themselves, and let me show you why. Here we have a typical printed circuit assembly with many components mounted on it. As you can see, there are many input-output pins on this assembly, and printed wires run from each of these pins to one or more components. If a static discharge takes place to one of these pins, it can zap more than one component. Our protection statistics bear this out. Over 70% of the parts which fail after they are loaded onto assemblies are those which are connected to input and output pins. These become freeways for electrostatic zap. It's time to summarize what we have learned so far. The first thing that we have learned is that static zap can be generated in both humid and dry environments. Secondly, we have seen that all types of parts are sensitive to static zap, not just MOS. In a related topic, we have learned that the zaps may not be catastrophic at first, but may merely wound the part so that it fails prematurely in the field. Finally, we have learned that assemblies are sensitive to static zap just as well as components. So now comes the serious question: what can be done to prevent static zap? The first thing that can be done is to set up static-safe workstations. Let's examine what that might consist of. A static-safe workstation can be anywhere: in receiving, the stockroom, assembly, test, even at the customer's facility. The important points are, first, to discharge the human body by means of a wrist or heel strap. Secondly, to eliminate these high static generators, such as the common plastics and the static generating tools. In places where those cannot be eliminated, an ionizer can be used to reduce static charging. And finally, but perhaps most important of all, to make sure that all personnel are static aware and trained in the proper methods of static prevention. Now, let's look at some of the materials and equipment necessary to build a static-safe workstation. For that, we will go to the demo area. Here is an example of a static-safe workstation. The first item you notice is the anti-static table mat, which is a resilient, conductive material connected to ground by means of this cabling. You'll notice that there is a safety current limiting resistor between the mat and ground to prevent the hazard of a shock. The second item in our arsenal of weapons against static is the anti-static wrist strap, which consists of two parts. A wristband, which is an elastic band with a stainless steel contact. I like to wear it with the contact on the inside of my wrist. The second part is the cable, which consists of a mating snap containing a safety resistor, the elastic cord, and a connector with which I'm going to fasten it to the table mat. Here in the corner of the table mat, I have a swiveling connector that allows me to make a strain-free contact with the mat. Now the mat and I are at zero potential. We've started our static-free workstation. In the event that a table mat is not possible, floor mats may be used. And I'm standing on an example of one of these floor mats. It's a material very similar to the table mat, and in the corner is a grounding snap, which you can see is connected via a cable to a snap on my table mat. Now the floor, the table, and I are all at the same potential. In the event that a table mat is not used, the floor mat may be grounded directly, but be sure to use the current limiting resistor. One problem occurs with floor mats, and that is that we don't know the conductivity of the shoe soles. To alleviate this problem, we have shoe grounding straps. Here is a sheet of 5 of these. To use them, you tear off one, fold it in the middle, place the shorter end inside a shoe, place the shorter end down inside, around the edge, put the part with the adhesive on the sole. Then when I step down on the table mat, there is a direct path through the strap to my foot inside of the shoe. There is enough perspiration in stockings to provide a good path from your body to this strap. The fourth weapon in our arsenal of tools is the anti-static desoldering tool. Here is an example of one. It differs from the previous one only in that it has a metallized barrel inside and out and a metallized tip. When this tool is held by the operator, you can see that there is no change to the reading of the meter. Even when the tool is triggered, nothing happens because all the static charge is eliminated. The last item is an ionizer, and this should be used as a last resort only when there is no other means to reduce static charging. Let's illustrate the use of the ionizer with our old friend, the Mylar tape. First, I remove a piece of tape from the roll. As before, as you can see, the tape is highly charged as it has been before. However, if we turn on the ionizer and place the tape in the air path of the ionizer for even a few moments, now we find that the tape is no longer charged. It has not been made permanently anti-static because I can restore a charge to the tape merely by handling it. But the ionizer will reduce the charge as we sit here and watch. Now that we have built our static-free workstation, we have another job to do. Let's go take a look at it. The second part of a prevention program is to make sure that all components and assemblies are stored in Zap-proof packaging. This consists of several parts, as we can see from the slides. First, we must prevent externally caused zaps by using a conductive outside package, sometimes called a Faraday cage. Secondly, we must prevent device charging by using only anti-static inner packaging and to pack tightly to avoid motion, which causes charging. Finally, we must be sure that the package materials we choose work over the whole range of humidity and are non-corrosive. Now let me show you how to do this. Here are some examples of conductive containers, which, if they have lids, can be considered effective Faraday cages. This little carbon-loaded plastic box would be an excellent Faraday cage. In addition, conductive, anti-static parts bins are available, tote boxes, tubes for integrated circuits, and even plastic bags. The only problem with these is that you can't see what's inside. The solution to that problem is to use a metallized plastic bag such as this one. The metallization allows about 50% vision, so you can see what's inside without opening it. The second step of the static prevention campaign is to eliminate the common plastics and substitute treated ones. Here are examples of a treated plastic bag. This bag does not generate static charge. Here is a block of foam, which can be used for packaging and padding. Here is a flexible foam, which can be made into a pouch or wrapped around the object. Tote boxes and parts bins are also available in these treated anti-static materials, as are the tubes, which are used for storing integrated circuits. Let me show you that this anti-static tube does not generate a charge. The third element in the anti-static campaign is to short all the leads of devices together where possible. Here's an example of an integrated circuit which is inserted in black conductive foam so that all 14 leads are effectively shorted together. This device is very well protected, providing only that the foam does not contain any contaminants which might cause corrosion. Similarly, you can protect a printed circuit edge connector by shorting the pins of it together with this carbon-loaded rubber clip. Now all the pins are shorted and the board is well protected against static. The final step in anti-static packaging is best illustrated by this metallized bag, and that is to label it. Make sure that the recipient of this package knows that he must only open it and handle the contents at a static safe workstation. You've heard a lot of information in a very short time. Let's summarize the important points. In summary, the important points were, first, that ESD is responsible for a significant percentage of our electrical component failures. Secondly, that ESD problems are likely to get worse as we use smaller, faster, lower power, state-of-the-art components. Third, that preventive measures are fairly simple, but they won't succeed unless everyone is static aware. And finally, that everyone who handles components and assemblies must take precautions all of the time. The last items that we studied were the use of the static safe workstation and the use of Zap protective packaging. With these two measures, we can defeat static Zap. Remember, don't make scrap, prevent Zap.